So we were saying that we want to find the expression of f prime xi using the backward scheme. So after rearranging terms, we will get the following. We will get that f prime at xi is equal to fxi minus fxi minus 1 over h plus h over 2 f second xi minus h square over 6 f third xi and etc. It's repeating itself. Okay, so here you will see that in this case we will have alternating sign, so it's plus minus. Why? Because delta x here is minus h. So when you have an even coefficient, the minus will cancel out, while when you have an odd coefficient, it will give you the result of minus. While in this case, in the previous scenario, all terms, so here, okay, when you just have xi in xi plus 1 minus xi, you always have the result is h, okay, it's h square or h cube. So the sign will not change because it's already you have a positive number that you are doing exponent 2 3 etc. This is why you here you have plus h square over 2 plus h cube over 6 etc. While in this case where you have delta x is minus h, so when you have delta x to the power of an even number, it will give you a positive result. While when you have minus h to the power of an odd number, it will give you minus h power the number. Okay, this is why here you will get alternating signs plus, minus, etc. Okay, so now when you obtain the derivative result, you will have plus h over, after dividing by h, it's fxi minus fxi minus 1 over h plus h over 2 f second xi minus h square over 6 f third, etc. But here also we can neglect these terms, all of these terms compared to fxi minus fxi minus 1 over h, because we are dividing by a small number, while here these terms are multiplied by a small number, and the highest error will be order of h, because as I multiply by h, the error is reduced. Okay, this is why also here we say that the truncation error is of order of this term, the first term, which is expected to be the highest term, and the order, it's of order h. And again, I repeat, the only assumption we are doing is that f second and f third are not very large numbers. So now we
Okay.
have obtained, we have derived how we can use from where we got the forward and backward scheme. And finally, okay, the centered scheme can be simply obtained using the same approach. So for the for the centered scheme, all I have to do is to add the two expression I got from the forward scheme and the backward scheme. And because I'm doing an average between the two, if you want, I divide by 2. So here, this is the expression of the forward scheme. This is the expression of the backward scheme. As an approximation between the two, if you sum the two and you divide by 2, then you will see that fxi will be simplified, because here you have minus fxi and here you have plus fxi. So you have fxi plus 1 minus fxi minus 1 over 2h, because you are dividing by 2. And what is nice about the centered method that we'll see here, we will see that the error will be reduced. The error will be reduced. Why? Because look, here, what will happen is that minus h over 2 f second plus h over 2 f second will simplify. So I will have that all derivatives that are of even order will cancel out, and I will just have the terms that will remain are the terms with odd order of derivatives. So here I will just have this term will be 0, and then the term that will be negligible, yani the first term that I will neglect, which is the highest one because it is proportional to h square, will be of order h square. So now my error was reduced, because in the previous schemes, forward and backward schemes, my error was of order of h, while in the center difference scheme, my error is of order h square. Okay, so this is why we will see together in numerical applications that the centered method will reduce the error. Using this method will reduce the error because in this method the truncation error is of order h squared, while in other methods it's of order h. Of course, if I'm talking about h smaller than 1. Okay, any question on this? So we continue next time. Thank you.